like administrative to-do lists that are like a year overdue. Not even so. Why am I gonna? I'm not gonna go and that's a exercise for the reader to fill in. Well, she has the video, right? And oh, you have the video, so maybe you'll do her a solid and add the stuff in. Make it. You can make a keynote, send it to me, and I will incorporate the slides. Mm, I don't think so. I had made that mistake one other year.
Oh no, doesn't sound good.
Yeah, we had some real-time jokesters because they were editing it during class. So let's see what class is this 450. It may have been larger, yeah. But now he's getting. He was spent all day yesterday at the VA having them check out his shoulders to see how much money the government has to give him because they never got repaired right. Yeah. So he was texting me last night how he was just like in excruciating pain because he just sit there twisting on it all day, and I got enjoyment out of that. I'm buying him wings tonight. We're going out for so I get enjoyment and I reward him. It's like a puppy. It's like it's the same thing. All right. Yeah, I don't think you can edit. Share options. Yeah, it's view only. Yeah, I learned that a while ago. But if you do send me some slides that you'd like me to put in this filler, I will say I'll do that. I might not, but I'll say I'll do it. like, what do you want from me? Okay, let's see here. We had our two different shared memory examples, and we've gone through those a couple times. So we've talked about some of the pitfalls. So we want to. Oh, that's the thing from the exam. Okay, so we were talking about race conditions last time. So remind me, what's a race condition? Go ahead.
Two objects or two processes try to grab the same object.
Yeah, two or more processes try to grab the same resource at the same time. So the kind of the mentality we want to switch ourselves into for this like last month of the class is all about protecting resources in the operating system, avoiding race conditions. And one of the big issues with race conditions that I think we really want to consider, and it makes them kind of difficult to work with, is they're often very difficult to reproduce. And that leads to bugs in software that are hard to trace back. You might have a race condition where something happens out of order and you didn't necessarily consider that it was a race condition that caused it. And you might go on this wild goose chase trying to figure out what went wrong and never actually find the error. But it might not happen again. And those are the most frustrating bugs, right? When something happens once and then it's never a problem again, and you kind of have to say, well, I think it's fixed, but you literally did nothing, that type of thing. So, race conditions can be pretty frustrating. Now, if we go ahead and draw our pictures, we might end up recreating some of those slides anyway. We want to have a situation where we'll just use two users for right now. This is user 1, this is user 2. So we have these two users. They're connected to a central server. All right, central server will then fork a process to deal with each of, so this is going to be a child of the server. This will be another child of the server. So these guys have a communication link here and here. All right, because they both connected to the server's IP address. Server created a child process. This child is now working with this incoming connections. They have communication back and forth, and we've done that. This one's working with this child. They have communication back and forth. All right, but now we want this guy to be able to send something and it get broadcast to everybody else. That makes sense? So that means we need to create a level of shared memory. Oh, that's not what I wanted to do. I want to do this. So this is going to be our shared memory. And shared memory is going to be established by the server, but is accessible from both children. So this leaves the PCB. So it kind of gets us into this idea if these three things are processes, all right, because these users might be using just a telnet session. We're not going to write a client for this, at least not yet. So these guys are just using a telnet session to test, connectivity to a socket server. So these are three separate PCBs, right? Historically, when we create some memory inside of one PCB and then we fork, we get a copy of all that stuff, but it's in its own memory space. It's memory space that belongs to the PCB rather than being memory space that has exited the PCB and lives at the operating system level. So we are relying on the operating system to provide for us the inter-process communication tools. The first one we're looking at here is shared memory, and we're going to review here the problem with it. Okay, so we have our shared memory thing that's provided to us by the operating system. So when this user, every single time somebody connects, this shared memory thing might get updated. Now, what might we store in this shared memory? We want to think about how chatting might work. So if this user says hello, they probably don't want to see hello spit back out to them because they already see it on their screen. You don't want to see it twice. But they want it to be broadcast to all of the other children, okay? Or all the other connected clients, rather. Okay, so when somebody connects to the server, we might start collecting. Terrible. We might start collecting sockets. So here we'll just say S1. And S2. I can't see worth anything today. Like even the S1 and S2 are blurry. Too much time in VR yesterday. All right, so S1 and S2. So this S1 might be the socket that's associated with this child. So we can actually draw some lines here just to kind of keep those in. So maybe this was the first child. And this happens to be that socket that's shared between them, that communication channel. Similarly, S2 might be the socket that is shared with the second child. But now both of these children have access to this shared memory. All right, so when this user says hello and their child server gets that message, that broadcast, because they're basically just sitting there listening, right? They're sitting there listening. So they receive that broadcast, and then they're going to go and say, okay, I want to now send that to all of the other connected sockets. So they're going to go to shared memory and say, I want to go through this, and every socket that isn't my connected client socket, I want to broadcast to that. I want to write something out over that socket. That makes sense? So this might be the initial plan, and we're going to see some problems with this plan. All right, so this guy is socket 1, so he's going to say, I want to broadcast hello. He's going to go through this list, the shared memory list, and see, okay, well, is this me? Yes, that's me, so skip it. Is this me? Nope. Broadcast, so over this socket, send the message, hello, which should then arrive at this guy's screen. Make sense? It should arrive at his screen, we're going to say right now, eventually. Because we have to think of the nature of these connections. right? So if you think back to what we've done so far, when we connected with Telnet, we've established a connection with the server, and then the server maybe initially spits something back to us. So there's this kind of back and forth cadence. So the server sends something to us and say connected. Then it's waiting for us to type something. And when we type something, that goes up to the server, and the server then responds. In our previous example, the server wrote something back out to us, right? But you have this blocking cadence where the server sends something to us, then waits for our reply. That make sense? So if we've sent hello here, and this guy has sent something, so or actually, let's say this guy has not sent anything yet. So this guy sends hello. This guy receives it, broadcasts it across all the sockets, tries to send it to socket 2 here. But nothing is being sent out here because this guy's blocking. So this child is waiting for this user to type something before it sends something over the socket. Is that going to be a problem in our current model? Who's actually broadcasting over the socket? Because this child right here kind of has a local variable that is S2. This child up here has a local variable called S1. How those two child PCBs operate with their sockets does not change the way that other processes can work with that socket. Just because this child here is waiting for the user to send something to him before he uses the socket, does that mean that this child can't use that socket? So we're thinking about a socket connection. It's a two-way communication channel between an endpoint. So just because the guy who originally kind of established it, let's say, is choosing not to write there until something is received, nothing keeps this guy from grabbing that communication. It was like grabbing, the megaphone from somebody. It's like, hey, hello! He's yelling into it. Well, this guy's going to hear it. Somebody else grab the megaphone. That makes sense? So now you have two separate processes that are trying to deal with the same resource. Is that a problem? Is S2 or S1, but our current example, we're talking about sending something, broadcasting to S2. Is that a resource we have to protect? Or is it kind of good that it isn't protected? Is it a problem if two different things are happening on a socket at one time? In your mind, we haven't messed with them at that level, but does that seem like it should be a problem? If it's a two-way communication pipe and the socket has not been the thing that we're using to block communication, the socket itself doesn't have this blocking pattern associated with it. It just so happens to be the people on the other ends of the walkie-talkies have chosen to wait for their little cadence. That's really a protocol, right? Server sends something to client. Server then waits for the client to send something back. Client sends something back. Server then sends it back to them. That was kind of our HTTP server, right? Okay. So we had established a protocol, a way of communicating between the two, so we made sure that the two sides received. So now it's this guy who's always receiving from this client. It's this guy who's always receiving to this client. But any of these other servers, well, in this case we have two. So this guy can always broadcast to this guy by directly using the socket, directly using that connection. That makes sense? All right. Now, something we're going to have to consider, though, is this socket was established at this server level, right? And then we went ahead and threw it into shared memory because we needed to store it there. Then we created a child process and handed it that socket for him to work with. Make sense? Is this a copy? Are these two guys pointing to the same place? Or are these two different sockets? When user 2 connected to the server, That established a socket, right? Then the server spawned off. It forked, created this second child. It was probably the second child here. Created this child. That child then has a copy of all of the variables that are associated with the parent. Is this S2 the same as this S2? Or are we actually talking down two different pipes? What do you think and why? You've actually seen this work. You just might not have realized you've seen it work when it happened. So if I'm the server and Annie's user 2, okay, she connects in. Now we've established a socket connection, right? So there's a connection here. But then what I do is I go ahead and I generate a worker for me. So that's Brennan. Now I still have that socket connection, but I've also given that to Brennan because we put Brennan in charge of now talking to Annie, right? And we've seen that work, right? That communication works. So at the very least, the copy functions. So then the question is, does the original still function? We have seen it function before, because what was the way we killed our server before? We went in and we stopped the server process, and then what happens to the clients? They get the little thing that says client server disconnected or something like that. So when we killed the original server, it broke off communication with everything else. That makes sense? So seemingly, the server, my original socket connection to her, and Brennan's socket connection to her are the same socket connection. Why? Why does that work when none of these other things seem to work? Why does that work fine without doing anything special when I needed to do this whole shared memory rigmarole in order to have stuff accessible by, these three different processes? There might actually be some truth to that, but it's not the reason for this. But there probably is truth to that. It would be the operating system's network subsystem that's managing that. So it probably is externally managed, but not the reason for this. I'll give you a hint. We'll see, and this is something I've mentioned in class before, but we'll see if you make the connection. The hint is POSIX. What a crappy hint. It's an excellent hint. Hint is POSIX. What is POSIX? I've mentioned operating systems before that follow what I've referred to as the POSIX standard. And then I've said what that standard effectively means. I think it's even in one of our slides. I think it's in one of the real slides, not the imaginary ones I didn't write. I don't want to scroll up yet because then you'll have the answer. But I think it's in there. Everything's a file. Everything's a file. Now, when we created our connection for our sockets, it's effectively a file. What variable type was a socket? Was that usually we call them file descriptors? A socket, an FD. What type is that? Cat, dog, or integer? It's an int. Now, do we, Alexis is like happy she got it right. So you had to choose between cat, dog, and integer. And you're like, it's an integer. Well, you might not, I might have actually believed that you believed that. See, she would probably be going first in senior. This Tim? No, I like Tim. I am a little concerned that you're on the second day, though. I don't know. I can't decide if I like you or not. Like, as a human, I'm a fan. All right. So we have integers, and we've seen. Now, first of all, we think about our historical background in programming languages. Are integers passed by value or passed by reference? Passed by value, right? We get a copy of it. So if I pass you the int a that holds a 5, and I pass you the int a that holds a 5, you both have a 5, right? And if she changes it, no big deal. If you change it, no big deal. But that int means something. So in POSIX-based operating systems, having a file descriptor stored as an int is effectively just a unique identifier. Think of it like your Falcon, your phone number, or your social security number, or something like that. Okay? It just points to some real file somewhere. And in a POSIX operating system, this idea of a file is a little different than our traditional thinking of a file. We think of a file typically as like, a Word document or a text file or something like that. But a file is effectively a data structure that's keeping track of some stuff. Now, the information that's stored in, let's call these the generic file descriptors in a POSIX-based operating system, is all the necessary information to support whatever subsystem is leveraging that file to solve a problem. In this case, it would be the networking subsystem that's working with sockets, and it's treating the details associated with this socket through this file that has a unique identifier that might be the number 5. All right? So if, back in our example, if I know that the communication with Annie is through the file descriptor 5, and Brennan knows that the communication with Annie is through the file descriptor 5, we both have access to the same thing because the communication is not happening. This is kind of where you were connected to the right thing. The communication is not happening through that integer. When I talk to the, I'm not talking to this integer. And that's kind of like that the movie with Tom Hanks and the basketball. He was on the island. What was it?
Volleyball.
Yeah, volleyball. Yeah. What was the name of that movie? Castaway. Yeah. You're talking to a rock there. I mean, that number 5 is not going to do a whole lot of chatting back to me. Okay? But when I go to the operating system and I say, I need to send something across, and I'm talking, I use the file descriptor, so I'm yelling at the operating system, I have a key. Okay? I need to send something to this guy. I don't even know what that means. It could be a real file. It could be a printer. Because in a POSIX operating system, everything is a file. So all I'm saying is I want to send something to number 5. Now, the presumption is that, in this case, it might be Brennan, who knows that it's talking to a real person over a socket. I mean, at some point, we have to make an assumption that we kind of know what kind of animal we're talking to. That way, we send the right stuff to that file. But I'm going to say, I want to send something to number 5 here, and here's what I'm going to send. So that value I have, the reason we can share it is that's not the actual communication channel. That's the unique identifier we need to find the correct communication channel at the operating system level. That make sense? So we don't have to worry about creating shared memory for these guys because this is effectively going to be a list of integers. What's going to be? A list of ints. No problem. And we don't have to worry about the blocking because even though Brennan might be sitting there waiting for Andy to say something, that's his job. His job in our chat server is for him to wait for Andy to say something and then for him to turn around and broadcast it to everyone else. That's his job. All right. So now, who wants to be our other server? Corey? Corey's the other server. All right, so Corey's the other server. So now, when user 1, so maybe you're talking, who are you talking to? Who wants to be the client? Gabe? Gabe's the client. Okay. Only Greek. Okay. You chat in only Greek. We're practicing, right? You're a Hebrew this semester. Yeah, Hebrew. Greek, you're done with Greek? All right, you can practice Hebrew then. All right, so you're Gabe's server. So you're sitting there just waiting for Gabe to send something, right? And Brennan's sitting there just waiting for Andy to say something. Now, Gabe puts his gibberish down on the thing, hits enter, you receive it, then you turn around, you try to yell it to everyone else. And what does that mean? It means hitting shared memory, going through and using each of these little, integers to talk to the network subsystem to send a message over that socket that doesn't belong to your person. That way you're not, saying something back to Gabe. So that's kind of the process. Now, unbeknownst to Brennan's just sitting there, just waiting for a communication to come in. He's just ready to read from that socket, waiting for Andy to say something. Unbeknownst to him, you've grabbed that same communication channel through the network system and just yelled down, just grabbed the megaphone and sent the gibberish, sent the Hebrew down there. And Andy's looking at it and said, I didn't even get the 80s references. Now am I going to understand the Hebrew? It's like, look, I didn't get the 80s. How am I going to get the zeros? And before the zero, the pre-zeros. You're not going to get those references. Or the symbols, probably. I don't even understand how my cousins read this Hebrew crap.
I can do Latin.
You do? Well, but he's practicing Hebrew. Why should he have to, change his cadence just to make you happy? Plus, I don't speak Latin, so that's not going to work. What do I speak? I speak English. I speak Telugu. I speak Urdu, I speak a little Hindi, and I know enough Spanish to order at Taco Bell. And there's a lot of those other ones were lies too. I tell all my Indian students that I know Urdu and Telugu and Hindi. I don't speak any of that. But I say I'm fluent, which then becomes funny when they try to say something to me and I try to guess what they said just based on the way they said it. And then every now and then I get it exactly right. They're shocked. But most of the time I get it very.
What stuff have they said?
I don't know. They're just normal conversations.
Okay, I wasn't
Like pass the soda or something like that. But I'll say no, I'm busy tomorrow. I pretend like I understood what they said. I didn't really understand what they said. Okay. So we kind of get our model here. Now, what weakness do we have in this current model? This is going to work to an extent, right? Where might a race condition exist in this model? It's not really a hugely problematic race condition, but it would be considered a race condition. Okay, so, if we say that we have 100 PCBs, right, instead of just 2, there's a chance that more than one person is going to be saying something at the, relatively the exact same period of time, and they're trying to broadcast to everybody, okay? So if we assume that Annie's somewhere on that broadcast list, okay, and you have 3 other PCBs that are all zipping down this shared memory, broadcasting to everyone except their client. Annie's going to be in all 3 of their lists because she's sitting there trying to still decipher the Hebrew. She's got the dictionary out and stuff like that. So, so now you have 3 people who are all going to try to send her a message at the same time. Is that a problem? And if it is, whose problem is that? It's reasonable for us to question whether it's a problem. But if it is a problem, it's probably the network subsystem's problem. The person who's in charge of that resource. Because we're not in charge of it. All we have is an integer. Right? There's not a whole lot we can do about that. So we're at that point, we're kind of reliant on, at least from a testing perspective, we're reliant on that networking subsystem of the operating system for that guy to be able to handle 3 or 4 or 20 different people all trying to access the same resource at the same time, creating some sort of pecking order, right? I think last time somebody suggested maybe we use I think it was Hinkle, that we create a queue. You suggested that? Yeah, so, these are some approaches we might take to protect that thing. But is that really a problem? What's the risk? What's the risk of if I technically tried to, well, I'm the server, so somebody else technically tries to send the message to her socket first, and somebody else sends it to her second. But because of how they, the network subsystem manage the multiple people connected to it at once, the worst that happens is the messages show up a little bit out of order, right? Maybe not the end of the world, especially if it's messages being broadcast from multiple sources, right? If you have 10 people saying hi, for example, and we have two kinds of messages on our system, either random stuff in Hebrew or just hi. And that's all our chat server supports. Okay. It doesn't matter what order the highs come in, right? And if you're in kind of a group chat room where somebody might ask a question, you might have another person who answers it. The expectation is the answer is going to be kind of intertwined in a bunch of other messages that are coming out. So maybe that's not so much of a problem. So assuming that, the problem would be if we miss a message, right? We wouldn't want to miss a message. But if we make the initial assumption that the network subsystem is going to do some sort of resource management for us and make sure that if you have 3 people vying for the same resource at the same time, they just handle it. Seems probable given that we're dealing with a modern operating system that has inter-process communication stuff built in, and that networking is a pretty important part of a lot of applications today. They probably have a fairly good infrastructure set up for their networking stuff. Okay. So what other race? So we could say that's a potential race condition, but maybe one that's not so much of a problem. What's another potential race condition we have here that maybe is a little bit bigger problem? Go back to that example where we have 100 PCBs, 100 clients connected, and somebody sends that message, says hello, and we're broadcasting it to everybody. And then during that broadcast, another client connects. Might we not send that message to the client, depending on how we're broadcasting, depending on how we're adding it to that shared memory list? It might be a chicken or the egg type problem, right? We might have already finished broadcasting. They may have already connected. And while they were connected and the new child was being born, the broadcast started and finished. And then they're added to the list. So they might be skipped over for a message. Is that a problem? Or is that just kind of the risk of walking into a room mid-conversation? Is there a legitimate fix to that? Do we want to fix it? Because in real life, it's humans kind of manage it, right? You walk in and say, everybody's laughing, and then you want to know, who said what? And then everybody has to repeat themselves, right? They're resending the messages, so we kind of handle it ourselves with that, because you didn't see old messages. What if we wanted to see old messages? So we think about the Slack model. When you join a room in Slack, you can see messages that have previously happened in that room, up to a point, because we're on the free version of Slack, so you only get a rollback to a certain point. But how might that work in our model here?
You have to store a list of all the messages that have been sent.
Yeah, so maybe have a shared list of all. When we do that broadcasting step, what we really do is we add it to kind of a queue of messages that have been broadcast. And then whenever somebody joins, we do an initial dump of that queue to their screen, so they get all the previous messages, and then they're picking up where they left off. Is that a reasonable solution? Not necessarily sure whether it's better or worse than just letting them miss a message and move on with life. Seems like if you're joining a chat room, if we think about this in real life, since we're trying to emulate a real life group conversation, right? If you walk into a room and all of a sudden you're just bombarded with all the conversations that have happened in the last 20 minutes in that room. That would kind of suck, actually, wouldn't it? You're not going to scroll back unless you're really just trying to catch up. Like 1 in 10 people are going to scroll back. Most people aren't going to care. So maybe for us, we just decide it's just not a big deal. You missed the message, you missed the message. But if you were already in the room, you were already connected, you shouldn't miss messages. Right? So the only point of weakness is that exact moment when you're being added to the list, when somebody else is broadcasting to the list. And we'll just accept that as a point of weakness because there isn't, we don't know if we even want to fix it. That's just the nature of things. Okay. Any other possible race condition? What about the list itself? We're creating this shared memory, so lots and lots and lots of PCBs have access to this list. Do we have a problem with multiple PCBs reading the list? That's not breaking the list, right? Having them access it isn't really a problem. It's when we modify something. That's when we really have to consider the ramifications of what's happening. Who modifies our list in our model here? The server. So even though all these other guys have access, and this is a choice we'll make, because we can make the wrong choice and say, oh, okay, I'm the server, I have an incoming connection, so I've created Brennan, and now Brennan's communicating with Annie, okay? And then he's going to go ahead and add, in this model, he will go ahead and add Annie to the list. Now, at roughly the same time, this other client joins. So Gabe joins, I create Newhouse, I create Corey, and he's going to then also try to change that list. Now we're playing with fire a little bit, right? As we're kind of considering, okay, well, what's the amount of time it takes to create a new child? Who's going to get CPU time next? Now, is it a big deal if the people get added to the list in the wrong order? That's not the end of the world. Okay? If Gabe happens to get thrown onto the list first, and then Annie gets thrown onto the list, even though Annie technically connected first, that's not the end of the world. The real problem is if both of them try to modify the list at the same time. That's the race condition. They've accessed the resource at the same time, and they both try to add at bucket 0 different values. Then it's going to be whoever accessed that last is going to be the one who left the... Okay, so all of a sudden we have Annie makes the list, Gabe's disconnected from the list, and all of a sudden he's never broadcast to. And he's wondering why he doesn't get any messages. It's like, dude, you're sending stuff in Hebrew. People aren't going to send stuff to you. It's a thing. Make sense? That would be a problem. So then we start asking ourselves, well, how do I protect that resource? Well, the most straightforward way of protecting resources in any situation is only let one person ever have access to that resource. We could put all sorts of locks and queues and things like that, like we mentioned last time. But can't we just say the only person that's allowed to change that shared memory is the server? When a new connection comes in, because we can only have one connection come in at a time, right? If I'm the server and Gabe and Annie are both connecting at the same time, whoever technically gets to that port first, I'm going to pick up that phone and I'm going to deal with that connecting client before I return to that phone and wait for the next ring. So Gabe's client is trying to connect while I'm I created the socket with Annie, I add her to the list, then I create Brennan, hand Brennan the socket, and then that communication has now begun. Then I return to listening to accept a new socket. That's when Gabe finally is able to connect. Now, in real life, that probably happened in some fraction of a second, right? But it was measurable time. And now, again, that new connection happens. I then add Gabe to my list. Only I am allowed to change the list. And I'm the only one trying to access the list from a change it perspective. Make sense? What about when people leave the server? How do you handle that? I mean, at some point we maybe make the decision, if we're going to try to create this as a simple list of connected people. Maybe we say the maximum number of people that can connect to our server at once is 100. Otherwise, we could create a linked list and have it be arbitrary, but let's just say it's 100. So we have our array. So now you have 30 connected people. So buckets 0 through 29 are filled. Okay. Then all of a sudden, person number 3 disconnects. When they disconnect, the child is then going to have to notify. It's going to have to modify that bucket. And what do? All of a sudden, we've introduced fire. So now we're saying, wait a minute. Before, only the server was allowed to change something. Now, we might have the child, one of the child processes, changing that list as well. How do we handle that problem? When a socket connects, and then, when a socket disconnects, all of a sudden that unique identifier is no longer valid. Correct? So even if we try to broadcast to that, we'll be talking to the wall until that identifier gets handed out again. Make sense? So it's not impossible, if a server's running long enough, for a socket ID, a file descriptor for a socket, to point to 2 different people. Maybe it was Annie 3 weeks ago, but now she's long since disconnected. Now another person connects in and just happens to get that same identifier. So we've thrown it back onto the list, never removing the old one. So for a long time, we were talking to the wall. We would try to broadcast to, socket 5, but it didn't go anywhere. We sent a message to the network subsystem. Subsystem looked around, said, I don't have anything, and then ended up just throwing the message away. But now all of a sudden it's going to a new person. How could we go through and mark this so that when somebody disconnects, they are permanently removed from the list? If the server is always trying to add the next client to the first open bucket, that is the first element in the shared memory list that has a null value in it, what's the worst that might happen? The worst that might happen is that the server's trying to add somebody, doesn't see the null early on because the server ran past bucket 4 before Brennan marked bucket 4 as being null because his client has disconnected. And then the server ends up placing the person later on in the list. So we say that's the worst thing that could happen. So the only bad ramification to that might be if you are at capacity, you already have 100 people in the room, and one person disconnects, but they disconnect just a fraction of a second too late. Then what ends up happening is the server says, I don't have any room for you, even though they technically did. That make sense? So, those are some of the challenges we have to deal with. All right, so on Friday, we're going to start writing this, and we're going to stop at a point, and then your homework over the weekend will be to pick up where we left off to finish getting this piece written. Sound good? Bible homework is already up. There is a risk of a quiz on Friday dealing with some of the stuff we talked about today. So no promises, but make sure you've reviewed the stuff that we've discussed today. Bible homework is up. It's due midnight Sunday. I put it up a couple days late. All right, I'll see everybody on Friday.